Alright, for legs, legs. Fellow mathematicians, welcome back to another video. Not gonna waste any time here because this video is going to be quite long. We are going to take a look at the last section of the Realschulabschlussprüfung in mathematics, Saxony-Anhalt here in Germany. If you don't know what I'm talking about, links to all the playlists, to the review of the exam, to the solution playlist. You can find all the links down there at the top of the description, in the info box, and also in the pinned comment. So we are going to dive right in with the first exercise. The picture below shows the Bismarck-Turm of Kalbe. With its height of 30 meters, the Bismarck-Turm in Saxony-Anhalt is the highest one of its kind. To build a tower, 1,600 cubic meters of brickwork were needed during the construction. For simplification purposes, we assume the tower to be of the form of a hollow cylinder with an outer diameter of 12 meters. So for this exercise to even approach, you need to know what a hollow cylinder is. And to be honest, it's basically just a pipe. Okay, so I'm going to draw a little sketch here. A hollow cylinder looks like this. So we have a cylinder here, okay, an outer one. And then on the inside we are going to have, well, yet another cylinder, you could say. And this cylinder is basically the hollow part, just like with a pipe, okay? Water is going to flow through it, and on the outside you are going to have either brickwork for this tower, or you are going to have like metal for a pipe. And this hollow cylinder has a height of 30 meters and an outer diameter of 12 meters. Using the diameter is kind of counterproductive, just because most formulas you will find with respect to the radius in your lookup table. This is what you can make use of here. So we are going to convert the diameter into a radius, meaning the radius, the outer radius, RO, I'm going to call it like this, is half of the diameter, meaning 6 meters. Okay, coolio. So we got some stuff ready already. So what is less information you can find here in this first text? Well, the brickwork used had a volume of 1,600, let's put it like this, sorry. I was thinking about 420 place it. So 1,600 cubic meters of volume on the outside. So this is like the outer volume we are going to have. Outer volume means the volume of this strip right here going around our hollow cylinder, our inner cylinder basically. Okay, with that stuff out of the way, we are going to approach our first exercise. The so-called enclosed space is an old metric for the volume that a building takes up in its completeness. Show that the enclosed space of this Bismarck-Turm is approximately 3393 cubic meters. So let us think about this metric, the enclosed space, at first. Enclosed space means this is the volume the whole tower is going to take up. Just think about like some kind of room we are having here. So on the one side you are going to have the space where you live, and this is about, let's say, 12 square meters. Okay, this is what I'm taking as a reference here. But what you also need is, if you place it on your property in some way, you also need to calculate how thick your brickwork is. For example, it's going to take up like, I don't know, 6 more square meters in a way. So translating this idea to our volume that we are having here, it just means that we have to basically calculate the whole volume of the outer cylinder. This is what you need to take into account, because if you place it on the ground, you have this brickwork here with a certain thickness. It's a thick brickwork here, and then you have your certain height that this whole thing takes up. So we are going to simply calculate the volume of this cylinder, of the big cylinder. I'm going to call it a volume cylinder big, CB, and the volume of a cylinder you can find in your lookup table is nothing but pi r squared times the height. It is what it is, meaning if we were to compute this, this is going to give us pi times, okay, what is r squared exactly? It's our outer radius, so RO basically. So that means we are going to have 36 square meters times the height is 30 meters. And we need to show that it's approximately 3393 cubic meters, and here's going to be the real value, and it's going to be pretty close to this. So we are done with the first exercise. Calculate the thickness of the brickwork. That's a thick brick that we are having here. And how could you calculate something like this? We are going to take a look at just our discs that we are going to have up here. So if we just take a look at this disc that we are having up here, this is going to give you a nice idea of what we are going to do. So if you look on top of the cylinder, okay, in a normal case you need to have perfect circles here, never mind. What is the thickness exactly? Well, the thickness of the brickwork is basically just this distance right here. But how can we calculate something like this? I mean, the only thing we have given is the outer radius. But what we also need is like the radius of the small cylinder, so like the inner radius, Ri. And thus our thickness, I'm going to call it T, okay, or just thick. Our thickness is just going to be the difference of the outer radius and our inner radius. So if our outer radius is 6 meters and for example our inner radius is like 1 meter, then 6 meters minus 1 meter is going to give you 5 thick meters of brickwork. So this is what we need to calculate. But how can we get ourselves the radius here? So how does this even work? How can we get the inner radius of this thing? Well, we need to play around a tiny little bit, because we could actually get the inner radius if we would know the value of the cylinder in the middle, so the small cylinder, VCS, I'm going to call it like this. And if we know the volume, then we also know the height and we know what pi is, then we can just divide both sides by pi and h, okay? And then we are going to take the square root and then we would get the inner radius of our small cylinder. But how are we going to even get ourselves this value right here? How are we going to get this VCS, so for the small cylinder, its volume? Well, it's actually quite easy. We are going to translate what we have here into our whole volume that we are having here. So from volume to distance. If we take a look, our outer cylinder takes up a certain volume. If we now were to subtract the volume of the small cylinder from this big cylinder, we would actually get the volume of our brickwork. But we know what the volume of the brickwork is. It's this. We also know what the volume of our big cylinder is. It's this. And with this we can actually solve for our volume of the small cylinder. So let us translate everything into what I just said. We are going to have that basically our outer volume was nothing but the volume of the big cylinder. So just what we did here basically translated to volumes instead of just distances. Minus the volume of the small cylinder. Cylinder small. Okay, and now we can just add VCS on both sides and subtract VO on both sides, leaving us with the volume of the small cylinder being nothing but, okay, we are going to have VCB is 3393 cubic meters minus, and then VO is 16 cubic meters. Okay, with that out of the way, we can actually go ahead and just start calculating stuff. So this is going to give us, okay, if we subtract this, we are going to get 1793 cubic meters. And this is our volume of the small cylinder. And like I said before, if we have the volume of the small cylinder, we can actually solve this equation, because the volume of the small cylinder is nothing but pi times h times the inner radius, what we are looking for, but squared. And now we can just simply solve this equation, leaving us with, okay, at first we are going to divide both sides by pi and h. So our I squared is going to be our volume, 1793 cubic meters divided by h, which is nothing but 30 meters, times pi. And now we are going to take the positive square root. It's only defined positive. And thus, we are basically done. You can also check for the units. So meter and cubic meters is going to cancel out to square meters in a way. And then take the square root of square meters is going to give you meters, exactly what we need. Then you are going to get yourself a certain value. And what we are going, the value you can find here. And after that, we are just going to plug it into here. And the difference is going to be what we are looking for, like the thickness of the brickwork. And that's it. A model of the tower will be built up to a certain scale. The outer diameter will be 6 centimeters. Calculate the height of the model and the scale. Okay, this one is actually quite easy. So putting up the scales here, it's not too hard. So at first let us think what our original diameter was. Our original diameter has been 12 meters. And now we are going to turn this 12 meters into 6 centimeters. So you can go two routes here. Either you turn the 6 centimeters into meters or the 12 meters into centimeters. 12 meters are exactly 1,200 centimeters. Okay, 100 centimeters are 1 meter, and this times 12 is going to give us 1,200 centimeters are going to be turned into 6 centimeters. Meaning overall, what factor do you need to scale this up to 1? So with which factor do you need to multiply 6 centimeters to get to 1,200? Well, obviously 200, all right? So you can just divide this 1,200 by 6, and then you are going to get that the scale is 1 to 200. Meaning, if we were to scale our 30 meters of height down, 30 meters are 3,000 centimeters, divided by 200 is going to give you 15 centimeters. And then we are done with this exercise. Next up is going to be an exercise which I find to be pretty cool because it basically includes just elementary number theory. It's about little Gauss. We have a certain function given, f of x, which is y, is nothing but 1/2 x squared plus 1/2 x, where x for now is element of the real numbers. And the first exercise wants us to evaluate f at the spot 4, x being equal to 4, by taking a look at our graph that we are having here, just putting our fingers next to the points, and after that putting the number 4 into this equation and see if we get the same thing out. So at first we are going to take a look at what we have here, f of 4. Okay, put your finger on the 4, put it up. Okay, it's between 0 and 20, meaning f of 4 is probably, as it seems, 10. It's right in between 0 and 20. How could we verify this? Well, by plugging the 4 into this formula. Meaning we are going to get x squared is going to turn into 4 squared, so this is 16 over 2. 16 over 2 plus, okay, 4 over 2. 16 over 2 is going to give us 8. 4 over 2 is going to give us 2, and 8 plus 2 in the natural numbers is 10. So this worked out, and thus we are done with this. That was really easy. So next up, a stack of equally sized boxes can be found in the shop. You can find the sketch here somewhere. You can also download this exam here, link in the description. Each new row on top of another contains one box less than the row below. See picture below. To express the number of stacked boxes with respect to the number of rows, we use the function f from above. Check the following statement. 6 rows contain exactly 22 boxes. So before we get into calculating this stuff or checking for the statement, I want you guys to get a hang of what y and x actually mean. So at first, what is the meaning of x? What does it correspond to? So if we take a look at f of 4, 4 was our value, our x value that we plugged in. And if we now take a look at this little sketch that we have here, what can you see when you take a look at 4? Well, plugging 4 into this function gave us 10. We have 10 boxes overall sitting here upon 4 rows. So this 4 right here is going to correspond to the rows that we are having in the stack. So this is the rows, the number of rows actually, and our y is thus just the number of boxes that we are having stacked here. So that's the number of boxes being stacked overall. There's also another interpretation for our x. As you might notice, the last row that we are going to get here contains 4 boxes overall. So you could interpret x as being not only the number of rows, but also the number of boxes in the biggest row, you could say. So this is also an interpretation here. With that out of the way, we can actually go ahead and see what we have here. Check the following statement. 6 rows contain exactly 22 boxes. Meaning, now we are going to take a look at what 6 rows are. 6 rows correspond to our x value here. So why not plug the 6 into our f? So f of 6 is going to give us, okay, 6 squared over 2 plus 6 over 2. 6 squared is going to give us 36. and 6 over 2 is going to give us 3, and 36 over 2 is 18, meaning 18 plus 3 is equal to 21, which is not equal to 22, so this statement does not hold. I want to show you something cool. With this expression that we have here, before we can go any further, this thing is actually called little Gauss. It's something that you find often in elementary number theory. It's an extremely important construct that has to do with Bernoulli numbers and all this crazy shit that you can find in higher mathematics. I would like to rewrite this really quick, because rewriting it is going to make calculations way easier for us, to be honest. So if we take a look, we are going to have x squared over 2, so y is equal to x squared over 2 plus x over 2, and you can see that we have a common denominator of 2. So let us bring this together. We are going to have x squared plus x over 2. And you now might notice that we have a common factor of x on both of these terms, meaning y is actually nothing but x times x plus 1 over 2. And this form is actually way nicer to deal with, because now if we were to plug in 6, for example, we are going to get 6 times 6 plus 1 is going to give us 7. So 6 times 7 over 2, 6 over 2 is 3, 3 times 7 is 21, and thus we are done. It's way faster, to be honest. So with that out of the way, we are going to make use of the picture above, that's next exercise, to calculate the number of rows needed to stack 120 boxes. Well, that's pretty easy yet again, because we know what the number of boxes are. They are just our y value. If we take a look at 120, go here, 120, and then go down to the x value, it's going to give us something between 14 and 15, 14 and 16, which is 15. So probably f of 15 is going to give us 120. Okay, this is probably what's going to happen here, but can we calculate this? Well, we can. If we just use this formula yet again. So if we plug the 15 into here, we're going to get 15 times, okay, 15 plus 1 is 16, over 2, 16 over 2 is 8, so 15 times 8, and well, 8 times 10 is going to give us 80, and then 5 times 8 is 40, 40 plus 80 is going to give us 120. And thus we are done, it does hold. And if you don't have this sketch given, for example, what you would have to do basically in an elementary way is to see that we have 120 boxes, this is our y value, meaning the question you could ask yourself is, for which x values do we have 120 boxes? So x squared over 2 plus x over 2. And then you could multiply both sides by 2, then subtract the 240 on both sides, and then use the quadratic formula. And then you are done. Just as a little side note, if you were too dumb to use this sketch that you had given here. Last but not least, in the context of the exercise, explain the meaning of x and y, as well as the change of domain of f. I mean, we are basically done with this. We have, in the context of the exercise, already explained what x and y actually are, but what about the change of domain of our f? So you need to know what the domain is. The domain is all the stuff that we plug into our function, into our machine here. So the domain are all the possible x values our function is going to take in. So now let us just take a look at the rows here. Would it make sense to have at first our x was element of R. Would it make sense to have negative 2 rows? Not really. It doesn't make too much sense if you think about it, negative 2 rows. Does it make sense to have half a row? No, it doesn't make sense. Does it make sense to have pi rows? No, doesn't make sense. Does it make sense to have 0 rows? Yes, it does make sense. If you have 0 rows, then you have 0 boxes stacked. So 0 does work. Does it make sense to have 1 row? Yes, it does work. Does it make sense to have 6 rows? Yes, it does work. And so on. So all the possible numbers we could possibly plug into here for the exercise to make sense in the context of stacking boxes is if we choose x to be element of the natural numbers, including 0. Okay, so we can have 0 rows, but we can also have 1, 2, 3, 4, 5, 1,000 rows. This is something that does work out. And this concludes this exercise. Now we are going to go for the last exercise, which I find to be the hardest out of all the 3. And I'm going to see you in a second. Alright, for the last exercise we are going to work a tiny little bit with the energy demand of a human individual and with the basal metabolic rate and stuff like this. Do not wonder why the basal metabolic rate is called GU. Here it's just because of the German word Grundumsatz, GU, Grundumsatz. Yes, that's the only reason. Here is like the explanation for the start of the exercise. look into it, and after you're done reading, we're going to go ahead and get started, which is now. So for the first exercise, calculate the basal metabolic rate, GU, of a 25-year-old female individual with a height of 165 centimeters and a mass of 58 kilograms using the picture above. Picture above means we're going to make use of this formula for the GU, which makes this whole exercise pretty trivial. So the GU is thus. Okay, so we have a fixed number in front, 655. I don't know why it's there, it's just there, right? Then we're going to have plus 9.6. Okay, M is the mass of the individual, which was 58 kilograms, times 58. And we're not going to put units in here because overall, this GU that we are going to get out is going to be in kilocalories. And well, adding kilograms to later time unit doesn't make any sense. So do not put any units there because this shit doesn't work out. You can't add different units to one now. It just doesn't work out. You can't add apples to pears, for example, just as a little example here. Next up, plus 1.8, and L is the height in meters, in centimeters, I'm terribly sorry, of the female individual, meaning it's 165 times 165. I need to change this. I put meters here instead of centimeters. It should be centimeters actually. And then negative 4.7 times the age of the individual, so that's 25, I think, 25-year-old individual. And this is some value that you're going to get out, and you can see it here, and thus we're done with this exercise. Next up, explain under the assumption that the given formula for GU holds, that we just use here, how the age of a female individual affects the BMR, the basal metabolic rate. Well, here we are going to do some approximations, because we only need to take a look at what happens if we kind of put a change into our age. So from 25 years to 1 year to 100 years something. Meaning all the other stuff can just stay fixed. It really doesn't matter for the point of this exercise here. So we are going to round up to some nice numbers such that we don't need to use a calculator here. So 655 is nearly 700. Okay, just using nice numbers here. 9.6 is nearly 10 times, and 58 is 50. Let's just use 50, I don't care. Plus 1.8 is obviously just 2 times, and 165 is just a meter flat, okay, 100. Minus, and 4.7 really doesn't matter, is 5 times our HT. And now we are going to calculate the stuff. So 700 plus 10 times 50 is 500, so that makes 120. 1200, I'm too sorry. Why am I saying 120 and stuff like this all the time? And 2 times 100 is 200, so this makes 1200 plus 200 is 1400 minus 5 times our age. And now we can go ahead and plug some ages into here, and then we can see how the age actually affects our whole GU in general, our basal metabolic rate. Let's say we are going to say T is 10, okay? We have a 10-year-old individual. So this makes 1400 minus 5 times 10 is 50. So 1000, so the GU is thus 1350 kilocalories. So what happens if we were to plug in T being equal to 20, okay? 5 times 20 is 100, 1400 minus 100 is 1300. Aha! Maybe we can already see a pattern. Let's exaggerate it a little bit and say that our Kr is 100 years old, okay? What happens then? Well, 5 times 100 is going to give us 500. 1400 minus 500 is going to give us 900 kilocalories. And you might notice a pattern here. The older our individual gets, the less, well, energy it needs, it demands, which does make sense. If you are a young krill or young boy out there, you need to eat a lot of stuff because you're running around, you are playing with your mobile phone and your Fortnite all day long, and taking a look at your grandma, she's a bit smaller than you, she's not really moving around too much anymore, so she doesn't need more energy than you need on a daily basis. So it does make sense. The older you get, the less you need to eat, basically, just to keep it nice and short. A female student, another female individual, with a PAL value of 1.5 has an energy demand of 2172 kilocalories. Calculate the LU of the magnificent grill. So we are now going to see what the LU is. The LU is going to be the active metabolic rate. And now here comes the hardest part of this whole exercise. We need to turn those sentences into formulas, which many students have a lot of problems with. So let us take a look at the first one and construct ourselves a system of equations basically. So at first, the product of the basal metabolic rate GU and the PAL value is equal to our energy demand. We're going to call the energy demand just E, and this is the product, so times, so GU of GU times our PAL value. And what is the next one? We have that our energy demand, on the other hand, is nothing but our GU that we are having here, summed up with our LU. Okay, coolio. So with that out of the way, we can actually start off with the exercise, because this magnificent grill has a PAL value of 1.5. So which formula are we going to use then? I wondered, the first one, and an energy demand of 2172 kilocalories. Meaning, for the first formula, we are going to get 2172 kilocalories being equal to the GU times 1.5. Okay, now we can divide both sides by 1.5, leaving us with 2172 kilocalories over 1.5 being our GU. And you can actually easily calculate this. If we divide by So 1.5 is 3 over 2. If we divide by 3 over 2, we are going to take 2/3 of this value here. And this is actually nicely divisible by 3. 1/3 of 2172 kilocalories is 724, meaning 2 times this is going to give us exactly 1448 kilocalories. Okay, really easy to calculate. And now we are having our GU, which we can plug into here. Meaning if we were to plug this into here, we have the energy demand given yet again, so that's 2172 kilocalories, being thus equal to 1448 kilocalories plus our active metabolic rate. And now it's easy to solve for our active metabolic rate. This is what we are looking for here, meaning our LU is thus 2172 kilocalories minus 1448 kilocalories, and this is just 1/3 of what we have here, so what I have talked about before, meaning this is going to give us 724 kilocalories. Okay, coolio. So this is our LU that we needed to calculate, and now for the last exercise, which I find to be kind of clever, this last exercise here. Now interpret the term GU times PAL minus 1 in the context of the exercise. Okay, let us write out what GU times PAL minus 1 actually is. So GU times PAL minus 1. GU times PAL minus 1. Why not multiply everything out? We are going to get GU times PAL. We have seen this before, right? Minus GU. GU times PAL. This is actually the energy demand of an individual. So this is the energy demand minus the GU. Energy demand minus the GU, this kind of rings a bell. Didn't we do this here? So this was the energy demand and this was the GU that we have calculated. So this gives us the LU overall. This is why I said this last exercise is kind of clever, because if you kind of didn't know what to do here, you could jump to the next exercise and maybe you were clever enough to solve this, and then you would immediately have like a formula for our LU, which you could use. PAL minus 1 in our context is going to be just 0.5, so PAL was 1.5, so 0.5, meaning we are going to take half of our GU, and the GU that we have calculated was exactly 1448 kilocalories. Just as a little side note, giving us exactly what we had here. And this basically concludes the MSA Saxony-Anhalt completely solved playlist thing that we had here on this channel. I hope you did enjoy what you saw. If you did, please like, subscribe, recommend channel. If you know about a few people who have problems in mathematics and you think that they could benefit possibly from the content here on this channel, then make sure to tell them about this channel, maybe also your teacher, and he will recommend it even further. And yeah, that's basically it. Thank you guys for watching. Up until the next video, I wish you guys a wonderful day. Ciao.